And yesterday you heard a beautiful presentation from Professor Thomas Ebbesen on light matter interactions. So we will continue today from where we left yesterday. So just to add upon, Professor Dasgupta yesterday introduced you the idea behind this webinar. So I will add a few lines. So during the pandemic, we all are passing through very, very difficult time. And one of the major challenge in the academic world is how to keep students engaged, academically engaged. So we were doing some exercise, and we have been asking students to do some literature survey and present some particular topic. And we felt, often students come back with very confused idea because the literature is flooded with large number of papers. This is where we both decided to start a webinar and invite a leading expert in a particular topic, and learn the complexities of the subject from a leader in that field. And so far, this has been fantastic, and we have been very fortunate to have a wonderful people. I think we had a very excellent series of seminar. And today, where we stand is today, Professor Thomas Ebbesen is going to talk, continue on a light matter strong coupling. So now I invite Professor Dasgupta to formally introduce to Professor Ebbesen.
Yeah, thank you, Satish. Thank you very much for those words. And it's a pleasure to have Professor Ebbesen again joining us for the second talk. For those who are joining us for the first time, just short introduction. Professor Ebbesen is a physical chemist. He was born in Norway in 1954. He got educated in United States and France, and he received his bachelor's degree from Oberlin College and his PhD from the Curie University in Paris. He then did his research in both US and Japan, most notably at NEC. And I think those were the ideas he talked about yesterday about drilling holes in templates in a dielectric. Before returning to France in 1999 to help build a new institute, ISIS, at the University of Strasbourg, where he currently is. He's actually the head of the Center for Frontiers Research in Chemistry and the Strasbourg Institute of Advanced Studies. He holds the chair of physical chemistry of light matter interactions and has authored many papers and has patents. And because of his pioneering contributions in nano-optics, he received the 2014 Kavli Prize in Nanosciences. And he's also, of course, because of the amount of novel work and fantastic science that he has done, he's honored as a member of the Norwegian Academy of Science, and he's also a foreign member of the French Academy of Science. So without further delay, I would like to invite back again Professor Ebbesen for his second talk on new properties of molecules and materials under light matter strong coupling. Yeah. Professor Ebbesen?
Thank you very much for the introduction. And so I'll continue slightly from where I started yesterday, but just remind you now it doesn't work anymore. I can't move my slides. So it's a strange thing. That may have to do with the YouTube projection. Okay, so yes, so yesterday I tried to make the point that something we don't learn in chemistry is that a lot of the material properties that we take for granted are actually influenced by electromagnetic fluctuations that occur everywhere in the universe, and they're called vacuum for meaning space, and they're in space, and they're called vacuum fluctuations. And what I'm trying to do, and the idea behind my research on this whole topic, is to use these, to modify this interaction with this vacuum field in order to change the properties. Somebody sent me an email saying that how can we get something from nothing? Actually, we are not getting something from nothing for nothing. We are actually just modifying the interaction with this vacuum field. And this is the important point. And this I will illustrate today with examples of modified properties. So in our system, we're under strong coupling. We couple an optical resonance and a material resonance. Optics and matter are treated the same way in quantum electrodynamics. And they exchange virtual photons, and they generate new states, such as these called polaritonic states, P minus, P plus, like coupled oscillators, and some dark states because we do collective coupling, and these hybrid light matter states, of course, redefine the whole ladder of eigenstates and therefore redefine the properties. The ground state is shifted downwards, acquires some photonic properties, and vice versa. So there's two papers, introductory paper. One introductory that I wrote is Account of Chemical Research in 2016, when a very well-known physical chemist, when a very well-known physical chemist told me to write about it so that I could reach chemists. So this is my account, this one, 2016. And just last week, we had a large review with 130 references in Science, which you can also read. So let me go to the next slide. So where I stopped yesterday is that after I made these whole arrays on the way, this was to do light matter interactions in cavities. I had these whole arrays made. They turned out to be very exciting plasmonic structures.
Thomas, I think we lost you.
Yes, he somehow just
frozen. I was wondering if it was only problem with me.
No. Yes.
No, it's a problem.
Sorry, we will like to tell everybody just to be patient.
Yeah.
We get back.
Just wait for a few seconds. I think probably he will be back. I hope he's not continuously speaking and he has realized. Yeah. Okay, now I think he'll come back again.
We lost you.
Yeah. Okay. So now he's back. We are back. Thomas, we can hear you now.
Okay, no. Should I go back?
You have. Yes. Could you again share the slides?
Which one?
So you were on the whole arrays. And you just started describing the fantastic plasmonic
array. Okay, sorry. So the whole array has plasmonic modes that can be controlled by distance.
The screen.
No, the screen.
Sorry, you have to share the
screen. Reshare the screen. Reshare the screen. The screen is unshared. We can't see your slides. Yeah, we can't see your slides.
Okay, so that's because we got cut. Okay, sorry. Then we'll start again.
Yes, and now full screen.
This is okay now?
Perfect. Yes, thank you.
So, what I show here is a whole array, and in a metallic film that supports plasmons, surface plasmons, which these structures were originally designed to put molecules in the holes, in the sort of nano cavities, half micron cavities. But in the end, it turns out that all we had to do is put molecules such as these J aggregates, crystals, on top of the surface. And we can strongly couple it in the dark to the plasmonics modes. Now, these modes also have 0-point energy. They fluctuate, and that's enough to generate strong coupling. So here you see this in a dashed line is the original plasmonic mode, and here are two modes, so they're displaced, and you can ask yourself why they're not coupled exactly at the aggregate absorption, and that's indeed they're not at k equals 0, as I point out last time. It doesn't look like it, but we do experiment slightly differently here. And we as a function of the plasmon mode, we can see that we have a Rabi splitting here, 250 MeV, and obviously this changes the photophysical properties of the J aggregates completely. And this we published in subsequent papers. This was our first understanding of this. And the important point here is we learned this very early on, so this is 15 years ago, that there are three criteria to show that you are absolutely in the strong coupling regime. The first of all is that the absorption that you're generating must be wider. The Rabi splitting measured in absorption must be wider than the full width outmax of both the absorber and the optical mode. In other words, they have to exchange virtual photon faster than the cake time of the components, just like classical oscillators. And the second point is that the dispersion curve should display anti-crossing. This is really important because some people now don't bother to test this, and they think they are doing strong coupling. Well, there are actually there's no strong coupling in their experiment. The last is the Rabi splitting should go in this collective as square root over n and the mode volume. So as square root of concentration. This is equivalent to concentration. A very easy test. So, so now I'm going to talk about give more details about chemistry first of all. So my contribution to this topic is that I realized that it should change. I was between optics and physical chemistry, and I understood that this should influence properties of materials. And the first paper we did was on electronic strong coupling with look at photochemistry. I'm a photophysical chemist by training, so it was obvious to me that if you split the excited state, I should change photochemistry. I'll show you some details after that. But in that paper, we realized that this was not so interesting for many chemists, a lot of chemistry. So we proposed in 2012 that if we coupled vibrations, maybe we could change chemistry, but having no idea if this would work. So here's the first experiment. We chose a very simple system, a photohybridization reaction between spiroperan and merocyanine, who's well studied and well described. They are very simplified energy diagram of potential energy surface of ground state and excited state. Here the absorption of the two isomers. And then we did the experiment in the same film. Then we spin coat a piece of the photochrome in a PMMA, dissolved in PMMA. We spin coat that on top of a mirror with an insulating layer to show the silver didn't do anything. And this all on a glass substrate. And then we had 2 points we measured through in 2 mirrors. So we have a cavity and a place we had non-cavity uncoupled, and we compared the two with time. And why doesn't that work now suddenly again? Okay. Then we make the measurement. It's a complicated analysis. It should be you can do the rate equation. It should be a pseudo first order. And when you plot the data, you see that outside the cavity, it's not linear, but it has a certain rate. The slope is the rate constant. But when you do it on the strong coupling, as you create more and more molecules that were the merocyanine, that were the ones that are being coupled to the cavity, as the number increases, the kinetics, the slope of this curve deviates from the non-cavity. Okay, and this nearly stops. Actually, it's nearly flat here at the end, and so you have as the square root of n increases, more and more molecules are coupled. The Rabi splitting increases, as shown here in this transmissions data, and the system stops. And in addition, the yield should increase if you look at the equation, if you do the rate equation. And indeed, when you lift off the top mirrors on the sample, which were made deposit on PDMS, you can actually see that under the mirror, even though it's hidden from light, there's more products than outside, which was very satisfying. It took 5 years for somebody to actually be able to predict the same thing theoretically. This coupling, so now I'm going to talk exclusively, we do exclusively now chemistry by coupling with vibrational modes, and you'll quickly understand why.
Thomas, there's a quick question. Question, Srihari?
Hi, I just wanted to ask, just before you go on, so in these cavities, you have a finite number of molecules, right, which are coupling.
Yeah.
So in these circumstances, can you still use macroscopic kinetic formulations for rates?
Yes, there's still Avogadro's number of molecules inside.
Oh, there's still Avogadro number, okay.
The huge concentration.
I see, okay.
Okay.
Thank you. Yeah.
So I will have a question slide at some point. So bear with me, I'll get through some pieces. Okay, so here, I hired a very good postdoc from Israel, Atef Shalabneh, who came from Raman, and he helped us start doing strong coupling with vibrational modes. And to test the system, we took a very simple CO stretch of this compound and to see if we could actually couple it. And it seems trivial now, but it was not trivial at the time. And we actually saw a Rabi splitting that got us very excited, about 20 MeV, not much, but still for us a step in the right direction. We need to understand how to make the cavities. We're now in the infrared. The cavities are much bigger. We need substrates that are transparent and so forth. And in the article, we speculated how it might affect chemistry. Of course, the immediate reaction of a lot of people was that this was impossible, including the referees. And it took us a very long time to publish. It's so long that somebody else was able to bypass us in the process. And And so could we do site-selected cavity catalysis, and so forth? Well, indeed, all these things were possible, and I'll show you now. So this idea of modifying chemistry with vibrations is a very old idea. Even in the 1950s, they had already understood this, not earlier. And in the 80s, Pimentel's group at Berkeley, who had the first access to infrared lasers, tried to do these experiments. They were able to do it, but only at very low temperature. Why? Because of internal vibration relaxation. So this is the difficulty of using it with real photons. The great advantage with strong coupling is you don't have this worry. There's no IVR in that sense. So how do we do the experiments? And I'm going to tell you a little bit how we do the experiments in these cavities so that you have an idea, because there are people trying to repeat our experiments. And except for those who have come to train in our lab for 1 or 2 days, it doesn't take more than about 2 days to learn how to do this. They then gone back to their home labs. They're able to do their own experiments on strong chemistry and strong coupling, but others suffer terribly and often publish wrong things because they are not able to. They don't quite know how to do it correctly. So the starting point, we have made a video because of this that's online at this site, at our website. We use these commercial cavities and a screwdriver, and that's all we need to do chemistry. This is an infrared commercial liquid IR for doing liquid FTIR experiments. And so there are 4 screws, there are spacers, and I'll explain the steps more detailed now. So here, you need a substrate. You have all kinds of transparent substrates, including diamond, which we also use for some very specific experiments. Silicon also works. And they're thick. And on that, we coat with gold or silver. And if you, for example, have 10 nanometer gold, you have a Q factor, the quality of the cavity, about 60, which is enough to do experiments. Mirrors need to protect it we've discovered very quickly that when we did reactions inside this reactor, the gold got eaten or the silver got eaten. So we now protect systematically our mirrors with SiOX or spin-coated polymer. Then you have this spacer here, and this is a spacer with a little hole in it. We have Mylar, Kapton, Teflon, and so forth. It depends on what you're doing and what you need, but those are commercially available and should be used in different thicknesses depending on which vibration you're trying to couple. Then when you have the empty cavity and you have these mirrors, you have 4 screws that hold them together. You tighten them with a screwdriver, as I just showed in the image. And in the process, you deform the substrate. And if you then look in the visible, typically against a screen, area of a screen of a monitor screen, you can actually see interference fringes. If it's balanced, the pressure on the 4 screws leaves a central area that's where the interference fringes show you that there's only all of this area is coupled, the central area is coupled. And as you move away, you essentially have new fringes, which are not on the strong coupling. So the area that's coupled is this central part. If you have a cavity that looks like this, you must start over again. It's no good. So this is a painful process because it takes some knowledge. And if you're Gino or George or Anoop, Thomas, then you know how to do this very quickly and very well. And even I know how to do it now because I sometimes carry one of these to other countries when I give talk to show people how to do it. So then once you have this area, this is the area you want to analyze. You cannot just analyze the whole area, which is much bigger than your beam. And otherwise you'll average over the whole thing. And so you put a cache, typically a little metal ring which you stick onto the holder, and you just analyze the central area. That's absolutely essential. In the time scale of a reaction, we have found by making tests or by analyzing the whole screen, the whole area, that there's no diffusion to speak of in the time scale of half an hour between the uncoupled areas and the coupled areas. Now, when you take the empty cavity and you measure the FTIR, you get a number of peaks as shown on this bottom right here, which are experimental data. And you see that the wave numbers are just given by, there's a constant distance between all these peaks, and that's just the FSR, the free spectral range for m equals 1. So it's here it's in centimeter minus 1, so that's why these units, and n is the index and L is the distance between the 2 mirrors. Very simple. And this is important to understand because, for example, you can have an absorption between two of these peaks and think that you have this is P plus and this is P minus. And because when you tilt the angle or something, they move because of Kramer-Kronig's relationship, and you're not in strong coupling regime. So then once you have done this cavity, you tune the empty cavity, estimating where the mode is needed based on the refractive index of the medium. This takes some skill. Then you take the FTR transmission spectrum, then you let it stabilize for about 20 minutes because these polymer films relax. And you take a new FTR spectrum and you fine tune it a bit further. Then once it's all stable, you check that the vibrational band is in the vibrational strong coupling. Then you do an especially in the beginning when you're not familiar with it, I highly recommend that you do an angular spectrum to observe anti-crossing and the Rabi splitting. And you have to watch out. So a split peak, you have reports in literature where people say they have strong coupling and it looks like this dashed line here. That's not strong coupling. It's not because you have split peak, you have strong coupling. Okay? You have to have a width. This width between these 2 points has to be greater than the width of the optical mode and the absorber. Then, I'm sorry to go through this, but I just want to give you an idea how difficult it is the first time. It's actually very easy afterwards. It just requires time. But a lot of people, because so many people have a hard time doing this, they think there's something suspect that only Ebbesen and his former postdocs know how to do this, which is not true, but this is what the current rumor are among some people in the community. So you stabilize the holder if you're going to do chemical reactivity at the desired temperature, using the same thing. You need a thermostatic jacket. They're commercially available. You inject a solution at the same temperature. The reactions should take about 30 minutes, ideally first order to make your life easy, or pseudo first order, because you need to premix the solution before injecting it. Of course, in the future, you'll probably have microfluidic systems that can do this, but for the moment, nobody has that. And then you take spectra at regular intervals. It gives you time to take spectra at regular intervals, for example, every minute. Volatile solvents should be avoided because they evaporate through the spacer. Temperature should be below 90 degrees for the same reasons. So how do you monitor the reaction? There are many ways you can do it. One of the simplest way we did was just to monitor shift in refractive index. The other modes that are far away from the absorbance bands of the compound, of the reactant, they will just shift as if the refractive index changes. So if there is a difference in refractive index between reactants and products, this is an exquisitely sensitive measure. You can detect very, very small changes very easily and very accurately. And then you can also do absorbance and fluorescence visible far from the IR coupling wavelength. But for that, you need to typically, then you have in the visible, you won't see much very, very well-defined fringes. So in the spectrum, so you can, for example, use a slit width that's sufficiently large to make them vanish. You typically use a large spacer, more than 12 microns thick. So those wiggles are tiny, and then you can easily do that. You can also monitor fluorescence, which we also do. And you can also do, which we have been doing in the last few years, an NMR directly on the solution. We inject the solution, we extract the thing, quench it or dilute it, and put it in NMR or mass spec. This works beautifully. So, any questions about this? Technical issues or anything else before I actually show?
Yeah, please ask questions.
If you have any, this is the moment.
Yeah. So I just wanted to quickly ask for one thing. When you're preparing these, so you said that all reactions are more or less done at 30 minutes. Why is that specific time mentioned? Because reactions.
Yeah, because you need time to mix the things before you inject it, so the reaction has to be over before you inject it. Okay. And you need time to follow it. You know, if it's too fast, you can't take spectra.
Sure.
You can do it longer, but then you have stability issues. So we have found that 30 minutes to an hour is sort of ideal.
Sure. Okay.
And so we arrange the condition. If you do pseudo first order, you can just adjust the concentration that gives you pseudo first order to the right concentration to let it dry
And typically these are millimolar concentrations that you try out?
Well, it depends. You have to look in our papers.
You have to, yeah.
But so there is if you just do pure material, you need very high concentration. You need liquid, so molar. But we have developed a technique called cooperative strong coupling, which I'll talk about in a minute, which allows you to work with dilute solutes. So let me show you.
Dilute solids, okay.
Yeah. So here was the very first experiment, which was done actually by Anoop Thomas, and in the cavities. So now here you have these mirrors, these substrates, the gold mirror, and a glass or some coating of glass or polymer. This was done with Joseph Moran's lab, who synthesized this molecule in variants, large number of variants. He's a synthetic chemist by training, and a young PI here at the institute, and he synthesized about 20 of these, and we to find one that was really what we wanted, okay, that fit all our needs. And that's the great thing in Strasbourg, is there are lots of synthetic chemists, and they help us prepare samples to our specification for our constraints, because we're in the proof of principle process still. So here you have the transmission. The red are the optical modes of the cavity, and above in blue is the absorbance spans of the PTA. And as you can see, we have tuned it so they can couple to this optical mode here, and the splitting is large. This is 860, and that's the carbon silicon vibration. It's double split because obviously there's also the SiC CH3 and the SiC here that both are interacting. And then we do the reaction on resonance, off resonance, meaning none of the bands are coupled. And then we do it, they are all in between. We arrange that. That's hard. That people like Anoop and Kalaivanan and Gino know how to do this. And then we do it outside the cavity. We always do a number of checks. Outside the cavity, off resonance, and on resonance. Then if we want to go better, we move across the resonance, as I'll show you later on. That's hard work. But what you can see is outside off resonance and outside the cavity the same. There's no cavity confined space effect, which you always have to worry about. But you see the reaction is slowed down. Here we just monitor the shift in one of these peaks that are far off here by looking into because the refractive index of the product is not the same thing as the reactant. So the slowdown, the reaction was kind of disappointing at the time, but then the postdocs came back and they measured the thermodynamics and got very excited because the delta H and delta S, the changes were gigantic. We went from 40 to 96 kilojoule for delta H of activation, and delta S even changed sign. Now, I didn't know that, but Anoop and Gino and other people in my lab knew that. I mean, the real chemists in my lab, they said this means that there's a change in reacting mechanism from associative to associative. And this was very surprising. Why is this very surprising? Because the Rabi splitting is KT, roughly the value of this term here, KBT. And we have splittings that are 10 to 50 times larger. We have changes, in thermodynamics that are 10 to 20 times larger. So how do you get this leverage effect? Okay, that was the first reaction of most people who are in physical chemistry. Where do you get the leverage? Because the perturbation of the Rabi splitting is tiny. So how does that influence the whole potential energy surface? Secondly, the vibration must be super strongly coupled to the vibronic interactions must be very strong for this to occur. So when this was made possible, oops, now I can go, sorry, now it moves by itself suddenly. Okay.
Yeah,
so actually this reaction that a lot of people, there are lots of theory out papers, they're saying there's no resonance effect, there's no this, because they use theories that are way too simple. And obviously you cannot, if you're a quantum chemist, you know how long it's taken to get quantum chemistry programs to the level that can predict reaction pathways and products and so forth. It's been 50 or 60 years in the making. And today we have fantastic quantum chemistry tools. For strong coupling, there are no such tool. The group that's made the most progress on this is Angel Rubio at the Max Planck Institute in Hamburg. I've been in discussion with him for literally 10 years on how to that we need calculations. I've known him from other topics before, and we have discussed about this, and he and his team has developed a whole ab initio QED DFT calculation package, which allows them to do amazing things. And so because they are ab initio and so forth, they have recently produced a result which is just remarkable. They actually show what's going on here in this reaction. And what they show is that the strong coupling, the vibration sort of redistributes the energy in many more vibrational modes, essentially in a very simple explanation, a simple version of their explanation. And therefore, the reactive pathway is sort of not favored, and the system gets stuck, and they have trajectories, and you can see the trajectory in the paper. You can go and look it up, and the system doesn't move forward, slows down. In addition, they show the resonance effect, which nobody had been able to see theoretically before, which we saw experimentally, and everybody sees, and for which we don't have a hardcore explanation. Even they don't, but they have a rough idea, partially because they modify the properties of the molecules in the process. So we then tried, obviously, the next thing to see if we could do site selectivity. So we synthesized this, Joseph Moran synthesized this molecule with 2 leaving groups. We had two transition states, and we wondered if we could modify that. And indeed we can, and we can inverse the yield. We start off with 80% of one, and 60% of one, and 40% of two, and we end up with 20% of one and 80% of two. And that was or the vice versa. No, that's right. And so, and of course, there are only certain vibration, and this is what impressed the referees the most, was this actually figure on the left. And indeed, it is beautiful, in my opinion. But you have to sort of be a chemist to understand the value of this, because you can see as Anoop tuned across this cavity, you can see that only 3 vibrations generate a change. So all these other vibrations, which you can also strongly couple, didn't do anything. And this is remarkable, because this is like an action spectra, and tells you that the obvious vibrational modes are involved. That's all the ones that were the CIS, CH3, the SIO, the SIC. Obviously, when you perturb those, you perturb the chemistry, and that's not very surprising. But it's still a proof of principle again. So then the issue was the fact that we need high concentrations is not great. And so for years we had been trying to think of a method to do this. Gino, when he was in the lab, spent a lot of time trying different things. If we could do something, I had this idea that if we had 2 absorbers of the same, absorbing at the same wavelength, it could influence, we could get strong coupling by mixing 2 molecules having the same absorbance. The physicist, my right-hand man who's a physicist, said in principle this is not possible because they are not quantum mechanically equivalent. So they don't add up in this theory the same way. Nevertheless, we tried all kinds of things, and when Gino charged this with vibrational mode, it turns out it works very well. And this you can understand why. So here, so I'll get back to the explanation anyway. So here what we do is with the CO stretch here is coupled at the same time as that of the ethylene acetate, the acetate here, ethyl acetate, and the CO stretch. And we use the ethyl acetate we couple essentially the ethyl acetate solvent. And because all the molecules are moving now in phase, like those metronomes, driven by the field, at least over a certain extent, each solute molecule senses nearby everybody moving in phase. And so it starts driving the CO stretch here. And this has now been shown also theoretically in this PRL paper of 2019. So here's the experiment. Here's the CO stretch of ethyl acetate. And here's the CO stretch of the compound, the reactant. And we get this big Rabi splitting. And when you do it off cavity, non-cavity, and then cavity on, you see there's a huge change in rate. This is observed in the visible. These experiments were done in the end, at least the last ones were all done in Mohali. And then we sent Gino some carbon-13 compounds to make sure that this was really a cooperative effect. And then he repeat the experiments with carbon-13 ethyl acetate, and then you see there's no effect. The reaction actually slows down, but there's no tuning effect because there's no overlap between the reactant mode and that of the solvent. So here you see again tuning experiment, you follow exactly the envelope. Okay, and this is at k equals s. We mean tuning, we mean at being at normal incidence, being coupled at normal incidence. So this was the very first experiment and on cooperative coupling, but this is a very powerful thing because then you can do all kinds of other things. Now, I can show you a whole bunch of other experiments, but I don't have time. If you want to, I can show you more. We'll see how much time we have. But I want to show you why we did finally an experiment, which I think puts the finger on what's going on in these experiments, why the effect is so strong. It was very difficult to understand, again, why a Rabi splitting of KT with a value of KT, sort of thermal energy, could produce such a large perturbation in the chemistry and the thermodynamics. So we studied this mesethylene-iodide complex, and which is a well-known reaction since 1940s. And this forms a charge transfer complex, been studied by very many famous people. Mulliken did the theory, he's a Nobel laureate. Zewell studied it, another Nobel laureate. And so this is a sort of prototypical molecule. And why is that interesting? Because it's very rigid, so the symmetry is very well defined. And I2 obviously this is not very important in this case, it's all in this donor, the donor molecule. And we can just study this equilibrium because this has a nice charge transfer band. And here's this charge transfer band of this mesethylene iodine complex, charge transfer complex. Benesi Hildebrand are the ones who originally studied these kind of complexes. And so there's something called a Benesi Hildebrand plot, which allows you to extract as a function of mesethylene concentration, you can extract the absorption coefficient of the donor acceptor complex and the equilibrium constant. And when you do this, you find something very surprising. So the first thing is, as you go up in concentration, you can see here, we were talking about how many molecules are coupled or not coupled. So here you have you increase the concentration of mesethylene and you have this slope, which gives you the equilibrium constant, and you're in a weak coupling regime. So essentially what you would see roughly outside the cavity. Then suddenly when you reach the strong coupling regime, boom, you change the slope. The points shift completely. You have a transition here. This is like a phase transition. Okay. So it looks like when you use strong coupling, the whole system changes phase. So this is one way of looking at strong coupling. And this is the first data points I know of this kind. And then Yan-Tao Pang and Noop Thomas studied many of these vibrational modes of mesethylene and coupled them in non-cavity and different modes of different symmetry. And when you do this, you come to this remarkable finding. I don't show you the tables, but here you have 5 different vibrational modes that were coupled. The ones of, if they were A prime modes, the equilibrium shifted towards the reactants. And if they were E prime modes, it shifted towards the products. And the amount of shift was nearly constant, independent on the nature of the vibrations or their energy, their frequency, which shows you the only thing that you are changing, the only difference is that the symmetry of the representation of these modes. And you see it here. Here is the thermal, this is now free, and it gives free energy. They change this equilibrium between the 2 ground states of these reactants and products. So here you see the changes. So outside the cavity, delta H and delta T, delta S are these values. You can see there are dramatic changes in this very simple thing again. Again, the coupling constant, the Rabi splitting is on the order of KT. So what this tells you, and I don't have time to go into great detail, but is that symmetry is central to vibrational strong coupling. And that strong coupling, the only way to understand this, if you spend enough time thinking about it, is that actually VSC changes the symmetry of the vibrational mode, changes it. Okay, and this we talked about yesterday about nodes and antinodes in the polaritonic modes. Well, this is probably related to that. And so this is obviously, when you study other systems that are more complex, other factors play a role too. I'm not saying that this is the only thing, but this is the underlying mechanism. Just like we know that symmetry from Woodward, Hoffman, Fukui, etc. We know that symmetry plays a key role in chemistry. That's why Woodward, Hoffman and Fukui got the Nobel Prize in the 70s, even though it's forgotten maybe now, but and also because most molecules you can't see the symmetry effect because there are too many other factors that hide it. So this to us was a very important result and show as a first key to understanding what's going on. So do you have any questions on this part? I'm going to switch from chemistry to other topics now.
Pranav, you had a question. Pranav?
I had a question about this cavity finish. You mentioned that you have 85% reflectivity and you showed that the Q factor is about 60.
Yeah.
That doesn't seem to be, I mean, 85% sounds like about 15, a finish of 15 or so. So what am I missing here?
Well, it's just one mirror. You have to remember there are two mirrors. I don't know if it's okay. So FD5 is an estimate. All I know is that we use 10 nanometer things. I can't tell you. I'm not the one doing the experiments, obviously. But we use about 10 nanometers. You can see through the mirrors, but you still get finesses that are good enough. Okay.
Okay. And so, So why is it necessary to have lower order modes coupling to these? Why only m equal to 1? Why not? So is there a scaling by which the effect decreases?
No, you can go to higher modes. There's no problem. We often couple 7th, 8th mode. There's no problem.
Mm-hmm.
Okay. You can couple other modes without difficulty.
Okay.
Srihari and then Liang. First, Srihari.
Yeah, thank you. Just two quick questions. The first one goes back to the one where you showed only 3 of the vibrational modes coupled in the silicon acetyl system. So do you know why those specific modes?
Well, because they are, okay, so let me go back. Where am I now? Let me go back roughly here, maybe. Yeah, that was lucky. Why? Because this is we are breaking this bond.
Right.
So it's normal that the SiC is sensitive to that perturbing this bond will probably influence the breaking of it.
Right.
Same thing here. Si, we are breaking this, so we influence it with the Si.
Mm-hmm.
Yeah. And the CH, probably by some induction effect, when we perturb this one, we probably perturb this SiC at the same time.
Yeah, I guess the quick question I was in the older literature of IVR. So there is something called as the heavy atom blocking effect.
Yeah.
So if you couple to something like where the silicon is with the acetyl mode, the energy would stay trapped there. It wouldn't get out of there so easily.
Yeah.
Do you think something like that is happening here?
No, I don't think so. I think it's different because we've done a lot of isotope effects on other systems to compare it to BSC, and it's always very different.
Okay. Second.
So unfortunately, I may be, but I don't think so. I think it just helps you to give an idea. I mean, IVR certainly is present in all the systems, but yeah.
No, I'm not saying whether IVR alone is driving it. I'm just saying it could be the fact that.
It could be. No, it's a good point. It's a good point, but we have no evidence of that.
But okay, my second question probably a little bit more provocative. You might have heard this question before, but when you were describing the huge change in the thermodynamic parameters, the delta H, the delta S, you're using sort of Eyring's equation, right?
Yeah.
Now the question is can you use Eyring's equation when you have vibrational strong coupling in vacuum in the cavity?
Why not?
Why? I mean, why should? I mean, it might not be that the transition state theory is in the same form here.
I know.
Was written.
First of all, it's linear. It's linear.
No, well, because something fits linear does not mean that it follows the
Of course not.
Yeah. So my question is that hypothetically, I mean, the way, of course, traditionally chemists think about Eyring equation is, of course, when you don't have the cavity and the sort of QED effect.
Okay, let me stop you just a second. The answer is very simple. Look at this graph that I have on the right-hand side. Why would the product yields change if the transition states didn't change?
No.
No, but listen to this. If the transition states, if the height that we measure, this change in yield here,
right,
okay, correlates with what we find from the I-ring equation.
Sure. I mean, but
yeah, so the products, you have to believe in the products. So if it's not, why wouldn't it, if it correlates with the product, then you'd have to kind of accept it. At least we accept it.
Okay. So there is a subtlety here, right? I mean, the result here, sure, you can interpret based on the I-ring equation, and that gives out these thermodynamic parameters for you,
yeah,
right? So that doesn't mean that the I-ring equation itself is, I mean, maybe some other equation which is more generalized.
Maybe.
I mean, that's why I said it's a provocation.
This is true for everything. You know, this is true for, you can say that strong coupling is classically, you can treat all strong coupling classically, but you can't predict any of this. You can't predict any products or anything. I mean, you can take any theory like that and say, does it apply to some other system? Mm-hmm. I think thermodynamics is pretty robust, and I have a hard time believing that their equation wouldn't. That's my view. But you would have to demonstrate that it doesn't. I mean, for the moment, we go on the assumption that things are fairly normal.
Sure. I mean, that's why I said my question is sort of hypothetical.
Yeah. But I think you. I mean, I understand that kind of question is part of being scientists, to be skeptical. But at some point, I must say, I've been hearing things for 10, 15 years about this. At some point, you get sort of tired. That you have to understand. You have people who say it's impossible. I sit in audiences with half physicists saying that there's no such thing as vacuum fields. The other half that says, yes, it is. I mean, I've heard everything under the sky here. People's careers been damaged by this. Okay, I have postdocs who's been blocked because some theoreticians think that it's impossible, that the Rabi splitting is what we see. It has to be redivided by square root of n. I mean, it's things like this, which if actually they knew more, they would know that that's incorrect approach to the problem. But because some famous, I mean, I'm just telling you, this is the problem, is that you get to a problem. Why I'm reacting like this is that you have to be aware that if you throw this kind of skepticism around to this point on a new topic like this, it's always very hard for the younger people. And for me, it doesn't matter. I'm years old, but
Thomas, sorry if you misunderstood my point angle was not that. I mean, mine was just basically saying that, you know, there might be sort of very new things happening here, which is that if we try to understand it based on sort of older theories, we might not be completely able to understand it.
Yeah.
You might be able to predict things, sure. Yeah. You might be able to extract parameters, sure. And perhaps that's why it surprises people that such large delta S change can happen.
But that's why I showed you symmetry. That's why I showed you symmetry.
Exactly.
Don't forget symmetry. I mean, I don't know what your background is, but symmetry plays a huge role in correlation diagrams. None of the people who did theory on this have even thought of it because they don't come from chemistry.
Sure. My background is IVR. So my background is IVR and vibrational coupling.
Okay. So maybe there's not a theory, but I mean, transition state
I mean,
pretty robust. Pretty robust, and I'd be very interesting if it didn't apply. But I really doubt it.
Okay. I just wanted to say that Srihari just gave the last ISCTF or colloquium on the IVR problem itself. So he delved into the IVR problem last month. So I just wanted to tell you that he comes from an IVR background. He's trying to put together things from that perspective. I don't think he meant to sort of.
No. But I'm just saying why I'm reacting the way. Of course, it's fine to ask questions like this, but I'm just explaining that at some point, people's career gets hurt.
Absolutely.
I've seen in the last few years, and we've had to fight for the survival of something.
Yes, I understand. Liang, could you ask a question, please? You're waiting. Liang Yan?
Yes, I ask a question. Yeah. Hello, Professor Ebbesen. This is Liang Yan Shu from Academia Sinica, Taiwan. I have several questions. The first is on like 21. Page 21.
Slide 21.
Slide 21. Yeah. So I found that in experiment for the transmission and for like a red curve and the blue curve, their y-axis is different. The scale one is from the 0 to 6, one is from the 0 to 100. Yeah. So I just wondering. So
What are you
because
talking
when
about? I don't understand. Sorry, I don't understand. What you say is 1 to 100 and 1 is...
Yeah, so for example, like for red curve, okay, inside the cavity, the transmission, the scale by is from the 0 to 6, okay. For outside the cavity, the scale by is 0 to 100.
Of course, because they okay, this is the blue curve is the absorption. We are just trying to show where the absorption falls, okay? So this red, the blue curve is scaled because it's absorption, okay? So we're looking at these dips, and this corresponds to absorption. So, you know, I don't know, nearly 80% of light is absorbed, or 90% of light is absorbed. And in transmission, it's just the transmission mode of the cavity, because the mirrors are highly reflective. It's not the same sample. It's not the same sample.
Yes. So my question is like because the two measurement is different. So if we compare them, this is
yes, of course, because the only thing you care about is the wave numbers. So you see this falls here, you see this there. That's not an accident, right? You couldn't get them on. It's like fluorescent absorption. You couldn't measure them on in the same machine. It's the same thing. We measure this without the mirrors to get a precise position of the absorption. How would you get these peaks if there was a cavity? Tell me. How would you do the measurement? You couldn't get these peaks because there'd be no light. There's no light transmitted here, right? So you couldn't do the experiment any other way.
Yeah, it's just for comparison. It's just for comparison with respect to the spectrum.
Yeah. So my second question is for like a FP cavity, you have like a cavity axis, like a D axis, but you still the photons still have like a degree freedom, like X and Y plane. So I just wondering like so when I read your papers, you think like a light have like a standing wave between like two planes, but actually photon have a degree freedom in the whole XY plane.
Yeah, sure.
So it's a good approximation to just think it's like a one dimensional, just the standing wave.
Well, that's of course. I mean, of course. Are you from optics, or are you from what area are you from?
Theory.
From theoretical chemistry.
Theory.
What?
Yeah. Theoretical chemistry. There's a
theoretical chemistry.
Yeah. So of course we assume there's rotational symmetry in the mode in the cavity. We're not polarized the light, so there's X and Y are the same to us. But we're not going to show. We show a one-dimensional thing just for simplicity.
Yeah, because recently I study like a resonance energy transfer, and I found that if the energy transfer maybe have the numerical simulation show like along like a XY plane, the energy transfer efficiency higher. Yeah, it's from the first principle calculation. So that's sometimes I was wondering, just for all papers, people emphasize like a cavity axis, but actually the photonic mode can couple along XY plane.
Yeah, but all the people who do this theory and experiment who already work on this know this. For you, it's new. I'm sorry to say, but to everybody in the field, it's obvious.
Okay. So, but just wondering. The third question is like page 22. Okay.
Next slide.
So you mentioned like Rubio group, they do some like QED density functional theory calculation, but I think they cannot calculate like entropy and enthalpy, like just calculate some internal energy.
Yeah, of course, but they can see what's going on in the trajectory. Have you looked at their paper?
Yeah, I just read their paper.
Right, so it's the best paper to date on the subject by all the experimentalists think so. Okay, it's very hard.
Okay, thank you.
The next level, if you want to improve on that, you have to quantify the optical field, and there are people who are now actually people in Europe who have managed to do that. We're collaborating with a group who has not only do you have an issue, but they quantify the field.
Okay. Okay, thank you.
Yeah, thank you. Shahzad.
Yeah. Hi, Professor Thomas. Can you please go back to your previous slide, number 21?
Yeah. Sorry, the wrong way. Sorry. Yeah.
So if I'm looking at your transmission spectrum, why can you please explain why you are not seeing any contribution from the uncoupled molecules inside your cavity? Or does it mean that
very good question? That's
does
a
it
very
mean
good
that you are
question.
having all of the molecules inside the cavity
Yeah.
getting
So
coupled?
I don't know if you heard me yesterday, but I explained yesterday that from experience, we've noticed that whether we align the molecules or not in the right direction, we get, when we have very large, strong coupling, it looks like most of the molecules get coupled. Okay, good 90-95%. Otherwise, you wouldn't be able to have a slowdown in reaction because all the molecules will go via the fast rate. So we have we don't know why it's like that, but it looks like you can couple at angles at off. You don't have to you can couple at numerous angles, perhaps except the very one that's where it's completely, except the ones where it's completely parallel to the field. And when it's not orthogonal, it doesn't interact. You can get most angles. That's the only explanation I have, but I don't have a simple one. The other thing that maybe is happening is the one thing I showed you on symmetry, where you see there's like a phase transition.
Right.
And it's possible when enough molecules are coupled, they influence each other. That's another possibility.
Right.
Like a magnetic field, when the spins start to align, and then it brings everybody else in alignment. I'll show you that later on. Okay, I'm going to show you magnetism results a little bit later.
Okay, sounds good.
Thank you, Shahzad. Thank you, Thomas. You can proceed, please.
Okay. I don't know where I was, but somewhere here. Oh no.
Yeah, after the question slide. Yeah.
Oops. Okay, I have to go.
Right. Yeah, thank you.
So I'm going to talk about materials now, okay? And then we can have more discussion. I have plenty more results, but I don't want to. So I'm going to talk about dressed materials. So dressed materials, dressed is a physicist term for describing they're dressed by the field, essentially the electromagnetic field. And so instead of calling it polaritonic materials, I prefer to say dressed materials, which comes from the atomic QED people. And here there's been a lot of measurements. I'm showing you ours, but there have been a lot of things. The first thing we measured was changing work function. You can actually see that, measure that. We modified the phase transition, not very so cleanly. We've changed, we can boost the intrinsic second harmonic properties of a material, the third order nonlinear properties of material, not just because of the cavity, but the intrinsic material. And then we've done quite accidentally, we have seen very recently, we just put this paper, came just online 2-3 days ago on supermolecular organization done by another very good PhD student from Aiser Mohali. And then we have done conductivity, and we're not just us, now other people find the same thing. This used to be believed to be unbelievable, but now there are at least 4 other groups that have seen this. So now we're not alone. Energy transfer poses less of a problem, though we show that you could do quantum entanglement. I'll talk about that, and then I'll talk about superconductivity and ferromagnetism. So let me start with supermolecular organization. So this was totally an accident. Kripa is supposed to look at conductivity on the VSC, and a Japanese postdoc in the lab thought that he could use some of the things he had during his PhD in Germany, some gel forming conjugated polymers that form gels, and that would be convenient because then we could measure the current as a function of make the gel inside the cavity and then on the VSC, and then measure the current on the VSC tuned or detuned. But when she did the experiment with him, she actually discovered that the conductivity dramatically dropped instead of not at all favorable. And when she looked more closely, she found that the whole organization of the material had changed. And this was just super interesting. So this took on. So here we do this cooperative coupling again, that we couple the solvent and dichlorobenzene, and it has a vibration. This drives the CC stretch of this conjugated polymer, and generates, and that you can see here, there's an overlap. And when we have this polymer, this PPE polymer inside the solution, it's in very small concentration, relatively small concentration. So you only see that when you take the IR spectrum here outside the cavity, it dominates the spectrum. And then these are the cavity modes, and here you see 6, 7, and so forth, 8. This is a double peak, so we split the peak in the peak again. I can discuss that later on, the meaning of that. And what she saw is that this polymer, when it forms a gel, has this very sharp peak, a bit like a jag you get, and it gives rise to this peak, and this peak has a fluorescence and so forth. And when she did it on a strong coupling, the whole spectrum changes. This peak becomes very minor. It slightly shifts. The isobestic point changes, pointing to a new product. And actually, when you see this was visible under a simple, nearly by the eye, here's the material on the normal gel formation, and here's on the cooperative BSC. We get flakes. So you turn gel into flakes just by coupling the solvent. So of course, we have done she has done a lot of other controls. If you couple just the solvent, other vibrational modes of solvent, you affect the rate of supramolecular assembly, but you always get the gel. But you can change but only on the cooperative do you get the change to flakes. We have other images. I'm not going to show them because I don't have time, but we have other images and other data, including isotope effects. And you can see that you can make a distinction between isotope effects and BSC. Now I should let you know that there's a paper by Hirai et al., a Japanese group, who spent 2 days in our lab 3 years ago to learn how to do BSC. Went back to Hokkaido. He's a so young associate professor, and he published first a paper on Prince reaction and showed that Prince reaction could be modified. And then he showed that MOF crystallization was also affected. He's from a MOF lab, a metal-organic framework lab, and of course it produces many. There are many forms of crystal forms, and to reduce the polymorphicity, he tried to do BSC, and he showed this. This is in its 6th submission. 6. Okay, it's in 2 years in the making. And why? Because you have people who say that it's not possible, impossible. And I feel really sorry for people like this, because he's young, he's trying to get ahead in his lab, and he's just being held back by people who just refuse to accept the data. And he has done so many controls, the SI is bigger than this paper. I hope that he will get it published eventually, but this is a remarkable piece of work. And this is also perceived, and just to let you know, industry is pursuing this. We have collaboration with the world's largest chemical company on this topic. So how about organic semiconductors? So I told you that we have these extended states. Potentially, we could have delocalized states that go over 100,000 to 1 million molecules. But of course, as somebody remarked yesterday, there's disorder. And of course, it never reaches that. The coherence length never reaches that far, except if you may be on a rigid system and everything is perfectly aligned. So, and at low temperature. So organic semiconductors, of course, are notorious for being exciting, but also having low mobility, relatively low mobility, even though they've improved immensely over the last 30, 40 years. But we are still far from silicon. And so I asked myself, I used to work for an electronic companies. I asked myself, why could we change this hopping mechanism, which is often the case, at least at room temperature in these organic semiconductors, by using these collective states. And could we do this first with electrons and then with holes? And so the electrons, we did that first, and that was when Gino was here. Gino was a key person in this, and then we used these hole arrays again, because when we first did with cavities, we saw some fantastic enhancement, 5 orders of magnitude enhancements in conductivity. Then it turned out to be some artifact. Then we got very scared. Then we decided to switch to a 2-dimensional system We measured conductivity along on a film that was on top of a whole array like this, and this worked much better. So here you have the absorption of these PDI. PDI is our top, the best semiconductors, and very good semiconductors. And then on the red and black are two transmission modes of this whole array. And as you can see, there are two peaks. And in the beginning, we didn't think of this. The measurements were done actually by the conductivity were made in the glove box by Emmanuel Orju, who was a young faculty member of our institute at the time and specialist on organic semiconductors. And when I told him, when he asked me what to expect, and I said, well, as functional period, it'll probably go up and down, and that would be it as you hit the resonance. And he said, oh, he came back the next day and he was sort of upset because he said, went up and down and up again. And I said, that's strange. But that it turns out is normal because there are two optical modes that crossed the material. And to understand this, you need dispersion curves. And so here's, take the bottom dispersion curve here. You have the absorption of the dye here, this blue, the PDI dye. And you can see it doesn't disperse with momentum. And here's 2 pi over period of the whole array. And here are the plasma modes of the whole array. And as you can see, the two plasma modes cross the absorption twice. They both cross the absorption, but at different momentum. And then when you go up here, you can see that they correspond exactly to the two peaks. And at those crossings, you have a huge ultra strong coupling, USC. And in the order of 0.7 electron volts. And you see a boost in current. And then we did another semiconductor, and then the maxima occurs are shifted. Now, they don't fall exactly because when you have such large absorbance in a material, if you know Kramer's chronic relationship, you know that near the absorber there's a tail that shifts the index and this distorts the spectra, the interaction, the point of interaction. The key thing here is that we made a gated system and allows us to show that the mobility is improved by an order of magnitude in the best one, in this one, in the PDI. We also tried a very poor mobility PDI, the brominated one, which is twisted and forms a bad material, and we can see no boost. So it doesn't work for all materials, as we have pointed out numerous times. Here, then we tried the P-type, and we collaborate with Anil Kumar from IIT Bombay, who provided us with this regio-regular P3HT, same kind of experiment, whole array, 2 electrodes, and substrate and so forth. This was done by, all the experiments were done by Kleivanen, and again, you see this crossing and enhancement to conductivity. We had theory done by Chuti. Chuti is one of the top polytonic theoreticians in the world. He's been at it for many, many, many years, much longer than we have. And is one of the first, actually it's the first person to say that ground state can be shifted if the strong coupling is high enough. Ground state can be perturbed.
Thomas, just wanted to add here that Anil Kumar is probably the world's best expert in making P3HT. His P3HTs are pretty much a gold standard in terms of regio-regularity, as well as if you just look at the material, it's completely silver. So it's beautiful stuff.
We were very happy to collaborate with him, and so this was great for us. And so, of course, when you do this, you can also look at photoconductivity, and you can see that there is enhancement. So the conductivity enhancement in P-type is not so great. And so you could argue, if you're a theoretician from physics, you would say, well, how can the ground state not be conductive because there's no photons in it? But actually, as Chuti, who's a theoretician, would tell you, is that the ground state has photonic content. It also is delocalized, and so it can contribute to the enhanced conductivity. And here you see the enhancement's not as great, but you can see that there's an enhanced absorption effect, because now you have a P minus P plus on both sides of this original absorption, so you can stretch the thing to the red. And the same thing is true for when we went back to the PDI, we saw the same thing, the one that's N-type. Since that, while we were trying to publish this paper by Kalevinan, it was refused three times at least before we found a journal that would take it. Jibink et al. From Penn State showed that photoconductivity can indeed be enhanced and very modified under strong coupling. So we are no longer the only ones, which is a relief. So So then I'm going to talk about another transport. Actually, this is energy transfer, and these conductivity experiments incited two groups to try to see if the electronic conductivity enhancement inside these groups to try to do energy transfer, which is easier to deal. And we, of course, were also interested in these experiments. So as you know, energy transfer is the first type energy transfer between donor acceptor, goes as R over to the power -6. And this means that over 10 nanometers, there's no more energy transfer to speak of. And I don't explain this to you because you are from chemistry or physical chemistry. But one thing that's unique to doing donor acceptors in the cavity is that you don't have to, but you can couple both donor and acceptor, which is what we did in this experiment, which was first done by Lizzie's group and much earlier than us. And what here we had the donor and acceptor, and then we couple to a cavity mode, which is over here, donor, and then we get a upper and lower polaritonic states. And then we take the lower polaritonic state, which is 50% photonic, so we can use that to couple that to an acceptor. Then we end up with 3 polaritonic states, upper, middle, and lower polaritonic states. Now, when you do this, the cavity entangles both the donor and acceptor, entangles in the sense of quantum mechanically entangle them. And that is what we were interested in, the most exciting part. Because that meant, you know, you can do all kinds of fantastic things with entangled states at a distance. So my idea was, can we use this to do energy transfer over larger distances than actually normally done? So when we did this, the first experiment, so I don't maybe have to explain everything here, but you know, often I talk to people I never heard about energy transfer, first type energy transfer. So you have donor and acceptor. This is outside the cavity. You excite the donor and you see emission from the donor and from the acceptor. Not surprisingly, because the energy efficiency is about 50%. Then you do it in the cavity, the same mix, and you excite again, and then you see just the emission from the lowest polaritonic state. Okay, and the efficiency has gone up phenomenally. So that's not a proof that you are doing energy transfer more efficiently. You have to see change in rates, and that Lizzie's group had not seen. So we decided to look for change in rates to confirm that energy transfer is really modifying. The donor is the efficiency has gone up, the energy transfer has gone up, which means that the donor lifetime should go down, or the molecule, that's the dynamics of the whole system should be improved. And indeed, the dynamics is improved inside the system. So we pump essentially the. Oh yeah. So I should explain one thing in addition. Sorry, there's one thing I haven't explained. One very important thing is that the upper polaritonic state is 95% donor, and the lowest polaritonic state is 95% acceptor. So when you pump the upper, it's like pumping the donor, and when you, in essence, you can think of it that way, and the lower polaritons is on the acceptor. Okay, so that's important to understand, because otherwise you won't understand why we're saying this. So the energy transfer becomes at least 90% efficient. And this has been seen also by Lizzie's group. Now, then we did an experiment where we separated donor and acceptor in space, because we know they're entangled. And we wondered, can we excite the donor on one side and see the emission from the acceptor on the other side? And again, outside the cavity, we excite the donor, we see emission from the donor, not surprisingly. And we see a little bit of tail, because from some direct absorbed by some direct excitation of the acceptor, and then we did the same experiment in the cavity. And what's remarkable here is that with the spacer level, this is the width of the spacer level, you can see that you continue to get energy transfer to the acceptor, to the lowest, from the emission from the lowest polaritonic state. Now, this, you can actually go further. The referees asked us to go further, so we went all the way to 200 roughly. And so we see a change in lifetime and the donor and so forth. And so we have an efficiency which is above 37% for molecules that are at least 100 nanometers. Now you might say, oh, but this is really real and so forth. Actually, we showed in the equations in this supplementary material that if you take the first theory, it becomes distance independent, okay, in this entangled situation in the cavity. And actually, just as the paper was going, it was going online. Garcia Vidal, with whom I collaborated with for many, many years, pointed out that they had published a paper in 2015, which they actually predicted this, and they hadn't realized it predicted this. But when he saw our paper, it reminded him of that, and so we added this citation to this 2015 paper. So it only depends on the systems being strongly coupled. And this, of course, is exciting. Why? Because it's the first example of a molecular process, at least in a laboratory, being affected by entanglement, quantum entanglement, which means that we could probably do other experiments under quantum entanglement. We could modify chemical reactions at a distance by quantum entanglement using cavities. So, questions? Then I come to the last part.
Yeah, Satish has a question. Satish, and then Professor Thomas, George Thomas.
Yes. I think perhaps this is my sort of a ignorance, but see, if the increase in conductivity in this conjugated system,
yes.
So inherently the low mobility in this conjugated system is due to these torsional disorder, a dihedral disorder at molecular level. So you see there is a disorder because you do not have coherent states. So this is the way we understand the hopping transport in a disorder systems. So can you please just tell us what happened at the molecular level when you say that the conductivity is increasing in cavity?
I think that the best way to understand it is we have these little domains that are coherent. They're not very long.
Okay.
And we over those little domains, maybe 10 molecules. The collectivity goes up significantly, and then we have some barrier again, and then it goes. We cannot overcome defects.
Okay, so
that's why the better the order, the more, and of course at room temperature, all these molecules are doing this anyway, so there's a limit of what you can do. But you have to remember that we have ultra strong coupling here, so the ground state has maybe 15-20% photonic character. It's very, very, it's a very unique situation.
Okay.
And there's another factor that you have to worry about here is momentum. Because we have not talked about that because chemists never worry about momentum, and I didn't either. But a lot of people, when we said this, but how on earth can you inject electrons into not only the right energy level, but you need to come at the right momentum, right? That's a solid state physicist view of things.
Yes.
And we as chemists, we don't worry about that. We just put two. We don't even use 4 electrons, just put 2 electrons, which is to a physicist is like, what? and so then I called one of actually there's experiments done by Vikovic and Tischler at MIT. Tischler is now a professor at Bar-Ilan in Tel Aviv, but Tischler, when he was a postdoc at Vikovic in MIT, they worked on photoelectroluminescence from polaritonic states in organic material, and they had the same problem, but they still managed. And so I talked with the referee reports, I couldn't understand them, and then I spoke with another very well-known polaritonic specialist and from solid state, and I told him what I was getting as comments, and he said, "Oh, that's because they assume that you need there's just one sweet spot, a tiny K and a T." But he said, in your system, your organic material is fluctuating all over. The K is not well defined, so there'll always be a place, so you don't have that problem. And this I never thought about actually. And so this is another point that if you get involved in this business, you will deal with when you see the kind of comments you get.
Yeah. So I think I was just thinking about, because there are absolutely no bands there, so you can't form a coherent state because of these fluctuations. So
but you can it's true. There's no band in the strict sense of the word, but there is a polaritonic state. Okay, and that is broad and drives the system. The theory, there's no problem with that. So I think, maybe it's a way of introducing one.
Okay.
Yeah, you can think of it that way. This is like entanglement. How on earth do you entangle molecules normally and keep them entangled? Here, it's very easy. So when I first present this entangled, people said it's not entangled because you don't do it the way we do it with atoms. And then somebody would, I give a talk at the famous quantum center. I won't tell where, but there were lots of quantum physicists were there. There was a debate in the audience whether that was possible or not. And afterwards, my host, was a very well-known quantum physicist, said to me, "No, Thomas, you're right. It is entanglement." Okay, so then I feel better about it. But their notion of entanglement is more like with atoms and so forth. Here it's a field. The field is entangling them, putting them in a coherent state, the two donor and acceptor. Okay, it's the same kind of issue.
Thank you.
Thank you, Satish. Professor Josh Thomas, and then I'll take a student question from YouTube. Yeah.
I have two questions from the energy transfers related to energy transfer. So you talked about the efficiency, enhancement in the efficiency. But what about the distance? How much distance you can go? Whether you're increasing the distance of
So I'll answer that first before you ask your second question. We only went to we have to maintain strong coupling, and we need to keep the conditions. That means we have to keep all this distance between the mirrors roughly constant, right? So as we make the spacer larger and larger, the thickness of the donor acceptor gets thinner and thinner. Okay, and so that's why we chose this mode that has a antinode at both in the acceptor and donor, so that because in the middle here there's no field, so there's no coupling here. Okay, people don't notice details like that, but that's really important in this experiment. And so obviously even though we favored this, at some point the layer will be so thin here that you're not going to get strong coupling. So as long as the theory shows, the better thing is to look at the theory. The theory says as long as you have strong coupling, you can do the energy transfer over any distances. Okay, as long as you maintain it. But technically, maintaining strong coupling over such distances is very difficult.
Good, thank you. And the other question is regarding the upper state and the lower state, tonic state. The emission will always happen only from the lower state, if I understand correctly. It cannot happen from the upper state.
Sorry, what?
No? Emission can happen only from the lower state. The lower polarity tonic state and upper polarity tonic state. The emission is always from the lower state.
Yes, because they obey Kasha's rule.
Kasha's rule. That is what I felt.
Something that many physicists don't even never heard about. I can tell you that.
Yeah. And the third thing is that the R�6 dependence, whether you are there is a change in the dependence to R⁵ or R⁴.
No, there's no more. There's no more. According to the equations we did and the theory done by people before, when you do it in this way, there's no more R dependence.
Okay, thank you.
Okay. Because you have coupling, essentially, you can think of it that the field overlaps the two systems.
Yeah, it's always coupled to the field.
Yeah, via the field. So normally you have to have this overlap.
Transition dipole.
The tail, but here the whole system is enveloped. That's one way of thinking about it.
It's enveloped. Thank you.
Two questions. One from YouTube. Kanad Mojumdar, who is a student from Satish's lab, is asking. I have often seen the absorptions to the P+ and the P- states are unsymmetrical, maybe in oscillator strengths or intensities. What is the reason and how can you control the oscillator strengths of these P+ and P-?
Okay, that's indeed, everybody sees that. It depends on the system. It depends on the shape. First of all, it depends on the absorption, the true shape of the absorber below. Often the absorber is not symmetrical, and so therefore that's one reason. One of the reasons. It also depends on other factors in the cavity. I don't know if there's one simple answer. You can take two optical modes and you find the same thing. Okay, if you take a plasmonic mode and you couple it to another mode, you get one intense, sharp, and one broad system. Okay, this is very common. So I can't remember. I knew the reason before because it appears in plasmonic structures, but I can't remember the exact reason. But there is a physical reason. But there's nothing to worry about. It's okay. But don't be mistaken. You need to be centered. If you're going to see an effect, you need to be smack on. You have to follow. The effect follows the envelope of the vibrational band.
Right. Okay. And the other question from a student, Chirag Arora, He's asking, could you please explain the role of the middle polaritonic state for the energy transfer, the donor-acceptor energy transfer?
That's a good question. I wish I had the answer. What would be the middle? I imagine the energy uses it to probably transits, maybe. We suspect when we did the transient experiments, when we did this experiment, we have indication that's the middle polariton dynamics we see. So you have to look at lots of details. It's very hard to explain that all in a few minutes, but the evidence points that the dynamics we see that shorten is the middle polariton. And so we believe the upper polaritonic state was too short-lived. And so we see the middle one, and that gives rise to the lowest, that feeds into the lowest polaritonic state.
Okay. And then we have Shahzad Alam again with a question.
My question is also related to the pump probes experiment. I was just wondering whether you faced any problem while conducting those experiments, because the percentage transmission from the cavity, I'm assuming, is very low, right?
Of course. Yes, lots of difficulties, okay? So if you want to do experiments correctly, the only way to do pump probe experiments correctly, whether in IR or in the visible, ideally you want to use, you cannot extract like we do. I used to do pump probe when I was young, and you just take the transmission, the ratio of the transmission to get the absorbance. You cannot do that, okay? Because you have too much reflectance. You cannot assume that the 1 minus A is the 1 minus transmission is the absorbance, or log of that. So you have to. I always recommend that we have actually Anoop went to the US, to Princeton, to advise people how to do experiments and so forth. You need to use a highly reflective mirror on one side and do it in reflection. So you make one mirror very thick, then you have to worry about the molecules being destroyed, the mirrors being destroyed. So you have to be very careful, especially if you use very high power, short time pulses. And so you have a sample holder that moves as you're doing the experiment. Right. And only if you do it like that can you interpret the spectrum. So we have a ChemPhysChem, it's Toll Schwartz from, I don't know, 2000, I can't remember when, 2010 or 11 or something like that, 12. That explains all the issues. When he tried to do pump probe, we encountered all of these problems. So yes, you have to be very careful. And also you mentioned that the laser beam can be bouncing back and forth inside the cavity, especially if you're using electronic strong coupling, and be very intense. So damage is a real issue. Raman's the same thing. The Raman, even if you see no damage to the sample, we did a Raman paper. It turns out the Raman signal we got is shifted, is modified, but the signal intensity is most likely due to some sears. We discovered that afterwards. We have just written another review, and where we discussed this point is that you can get the gold can just melt enough to form little islands, and this of course can change a lot of the signal. Sure. So you have to be very careful.
Good, very good. Response. Thank you, Thomas. Shahzad, thank you for the question. There's just one comment Chirag Arora just made. If you increase the density of states of the middle polaritonic state, would it enhance the energy transfer?
No idea, but a very good question.
Okay. Yeah. Okay, Chirag, there you go. Okay, so thanks, Thomas. Let's move forward. Yeah.
Yeah, so the last part. So the last part is just about two material things. Again, with molecules, but not just molecules. And some of this links to work done in Bangalore. So this is kind of amusing. So I used to work on C60 superconductivity when I was at NEC. We set a record with rubidium cesium C60 in 1995 or something like that, 94. And when I realized that we are softening the vibrational modes by vibrational strong coupling, we thought, well, can the TC change? This seemed pretty obvious because C60 is a phonon type superconductor which stabilizes the Cooper pairs. And as a control experiment, we chose to use YBCO. YBCO is not a phonon superconductor, it's a high TC superconductor, and the mechanism of how it works is not still a debate, but certainly not a phonon one. And then how do you couple these? A lot of problems of coupling inorganic materials is the fact that they're very weak. They have very weak absorption phonon bands, and so it's not easy. So we decided to try polymers. Actually, we tried to do it in the cavity, to be quite honest, but the control experiment on single mirrors showed us a change in TC. And so then we realized that we were just coupling to the surface plasmons of the gold mirror. And so we switched to one which much simpler sample, because we can lower the sample. We don't have to worry about Fabry-Perot modes. We just put the superconductors or the material in a polymer that's on the cooperative coupling with the superconductor we changed, and it interacts with the surface plasmons of the mirror. And then as we put it in a squid and go down to 4 Kelvin, there's no distance issues, and as long as it stays stuck to the surface, we can measure TCs. So then we did the experiment. So here is this is Anoop, among other, Anoop and somebody called Eloise Deveau in my laboratory who did all these experiments, and you need great patience, which luckily they had. And so here's rubidium-3C60. It has a little phonon band here, and that we couple to polystyrene. We use the polystyrene to do cooperative coupling. We just control PMMA. And what you see is that, and you look at dispersion, reflection, you see anti-crossing, actually a double one, because there are 2 peaks here, but only one, we're only interested in one. And what you see is that when you do it with polystyrene and rubidium, the TC is what you expect, 30 degrees essentially. When you do it on polystyrene on gold, the TC changes to 45. And when you do it in PMMA on gold, it goes back to 30. And this, of course, was very exciting. It was a 50% increase in the TC. Here's the statistics. We did many samples. As I said, the experiments are extremely difficult to do correctly. It's hard to imagine how difficult this is. And then you see that there's a peak here at 45. Now when we submitted this paper, this was okay. This was fine. This didn't bother people. But what really bothered them was the referees, was the fact that we had used YBCO as a control. And the YBCO material also changed TC, but in the opposite direction, went from 92 to 86. And how on earth could this be possible? These were not phonon, there were no issue, the phonons weren't playing a role in here. So how could they change the YBCO? This was just unacceptable to the referees, but it's a fact. You know, this is the problem a bit with modern refereeing, is you have this data, and it's because it's, you know, all new data seems unbelievable if you've never done experiments like this before, but it's real, and we have enough controls, enough experiments. And again, you see that it turns out polystyrene also has a band which overlaps with a defect band of YBCO, which is present only in YBCO powder. And so the paper was refused, and we went back to more experiments. And so it turns out there was these 2 guys are specialists on magnetism. They looked at our data that was online. Marc Trion is an old friend, so he contacted me and said we have to discuss this. And he realized that there were actually a ferromagnetic signal in our particles. And it turns out actually that, and Rao and famous Rao, CNR Rao and his colleagues in Bangalore had shown many years ago, not only them, but that inorganic particles, oxides, could often be slightly ferromagnetic, weakly ferromagnetic, and this was understood to do with defects in the surface of these nanoparticles. And these particles we were using were 200 nanometers in diameter. And so then with that, things became clear. So what happened? So we studied the magnetism. Here's my Bohr magneton's functional field, and what you see here is the changes when you do. Here's the condition where you see a change in TC. There's a huge change. There's a huge ferromagnetic signal which survives at room temperature. It's quite remarkable. So look at the difference between here and here. You can't even see this stuff on this without the gold. And the gold alone, of course, the other things. If you take anything out, we've done all the controls, you see this. It turns out the hysteresis depends on the thickness of the gold, as you expect. And because of the surface plasma modes, quality changes. And this is just like you would for, using surface plasma sensors. It follows exactly what you expect. And in essence, what you have is that the ferromagnetism has gone from being absolutely negligible to becoming nearly close to 1 Bohr magneton, and increased by a factor of a whopping 700. Okay, and this is truly remarkable. It means that the vibrational coupling, which is driving all these things in phase, also drives the spins. To me, this is unbelievable. I mean, if anything is, it's real, but it seems absolutely surprising to me. How does the phonon modes that we couple drive this alignment of the spins? But this is amazing. So you go from something that is totally negligible ferromagnetism to something that resembles a magnet, and the data is super clean. So this for once was very easy to publish. It took us about 3 weeks to get it accepted because the referee and the editor were excited about it. So this is to show you there's anything you touch with this. I think I've shown you that you can change chemistry, intermolecular interactions. You can change the solvent properties. You can change enzymes. You can change conductivity, magnetism. You can change just about anything. Why is this? Because I come back to this, what I started to talk about. You're changing matter. The material properties as we know them are determined in great part because of their interaction with the vacuum field. And by doing strong coupling, either weak or strong coupling, we are modifying that interaction with the vacuum field. And therefore, we modify properties. So it shouldn't come as a surprise. It only comes as a surprise because we are not taught that the vacuum field plays such an important role in our studies. Okay, and that is my conclusion of my talk. So there's light in the dark. That's what my message is to you. There's lots of things to be done. This is just the beginning. It's the tip of the iceberg. Lots of theory, but theory has to be done with very precise tools, very finely developed tools, and that are just coming into existence right now to be able to handle the more complicated things. The simpler things from a theoretical point of view, of course, are the phase transitions, superconductivity, magnetism, transport. But the chemistry is very hard to deal with. And I want to finish by recognizing all the people who worked on this. So in the very beginning, there were 2 people absolutely critical. James Hutchinson was back in Melbourne, and Tal Schwartz is a professor, or a young, I don't know what they call, senior lecturer at Tel Aviv, tenured, for the electronic strong coupling.